So today we have the pleasure of welcoming Pierre Charollois from Sorbonne, who will speak on Eisenstein's Jugendtraum for complex cubic fields.
Thank you. Thanks a lot for the invitation and giving me the opportunity to give this talk about joint work with Nicolas, Bergeron and with Garcia. So we came up with the title, with a kind of a provocative title about Eisenstein's Jugendtraum. So I will try to convince you that there is a Kronecker's Jugendtraum that is well known in number theory, and that I will try to convince you that there was a Jugendtraum by Eisenstein as well that was even former than this, and they are both related. Okay. So let me first recall the very statement of Hilbert's 12th problem as appeared in the English translation. Hilbert wanted to discuss his problem, and this problem has joins three different fundamental branches of math: number theory, algebra, and function theory. And he was certain that the theory of analytical function of several variables would be enriched if we succeeded in finding and discussing those functions which play the part for algebraic number field corresponding to the role that was played by the exponential function for the field of rational numbers and of elliptic modular functions, the imaginary quadratic case. This is still very much of an open problem. And to begin with, the core of my talk will be devoted to complex cubic field, but I want to start with the classical case where K equals Q, or K is an imaginary quadratic field. And I will review the work of Kronecker-Weber, the theorem of Kronecker-Weber, and the theory of Tane-Mashimura very briefly. So over Q, the statement is that any finite abelian extension of Q sits inside a cyclotomic number field. And so we can write down square root of Q as linear combination of roots of unity. And And what we will be mainly interested in are units. So this is the example of a cyclotomic unit. If A and F are coprime integers, then UA of F, being 1 minus exponential 2 pi I over F, is a unit that has, or more specifically a F unit, lying in the ring of integers of the cyclotomic field. Okay, so those are the kind of units we're after. Now, the case of imaginary quadratic fields, then the story for Kronecker's Jugendtraum starts with modular units. So a modular unit will be typically eta of tau divided by eta of n tau, which has symmetric group gamma naught of n, and is given by an infinite product that's nowhere vanishing. Okay. And more generally, you can take certain ratios of such functions, and these are called modular units. And if you want to generate class fields out of this function, then you would need to evaluate these modular units at an imaginary quadratic number. And then you would obtain units sitting in abelian extension of the ground field K. A little bit more general is the case of elliptic units. So they are designed out of this specific function. This function will play a major role in the lecture. This is one of the Jacobi theta function, maybe one of the. So theta 0 has an elliptic variable and a variable in the upper half plane. So I write it as 1 minus q times the product of 1 minus q to the n exponential of z, and then 1 minus q to the n exponential of minus n is bigger than, I guess. Yeah. And I will devote a bit of time describing the symmetries of this function. So you have one periodicity with respect to z, almost up to a sign, and almost two periodicity, up to a certain exponential factor. Okay, these are the periodicities for the elliptic variable. It does satisfy the distribution relation. So there is a certain distribution relation that it's very useful for Euler systems. And then there is the modularity property under SL2Z. So it's one periodic in tau. And there is this very peculiar modular transformation where z becomes z over tau, and then tau goes to -1 over tau. You get the same function up to an exponential pi I times a factor which is a rational fraction of tau and a polynomial in z of degree 2. So that's very classical, but you will see that we are aiming at kind of generalization of this identity for SL3Z. Okay, so I want to discuss the CM theory out of this function. What people do, you will evaluate theta at tau 0, again a CM point. But to have nice properties, you need to take this kind of ratio. I will call it a smoothing. So I fix a certain integer n, which is a norm of an ideal in OK. And I will take this ratio, theta to the n, divided by theta, and I multiply each argument by n. Now the periodicity is much better with respect to z. And the CM theory is when you evaluate this variable, this function of z, elliptic function of z, at a torsion point in K, so at certain point in K, then the outcome is again a unit lying in a very specific class field of K. Okay, and there is even a description of the action of the Galois group in terms of Frobenius. So Frobenius at C acts in a very specific way. So it's the analytic theory of units. Yeah, it's explicit class field theory for imaginary quadratic fields. And I would summarize this as saying that this solves Hilbert's 12th problem in the case where the ground field is imaginary quadratic. Okay. Moreover, yeah, these units are also connected to partial zeta values, or even more specifically to first derivative at s equal to 0 of partial zeta functions of K. And in that sense, it's done through the famous Kronecker limit formula. And in that sense, these elliptic units are the prototype of Stark units. Okay, I will come back to the partial zeta function later in this talk. Yeah, so I wanted to give some example, in fact, some numerical examples. So I take specifically Q of I and then a certain theta ratio, and I will compute with my computer that many digits and try to convince you that this is an algebraic number. So there is.
You told me you're going to do some live stuff.
Yeah, it's like demo. So that
I don't want to see numbers computed before.
Yeah. So supposedly, let me show you. So you agree that tau 0 is this number, and the numerator is going to be this. So copy. So it is computing the theta 0 at 1 over 6 and then 2 plus I over 4. And the denominator is much the same, except that I multiply each argument by 5, right? So take this number 5, it is computing, and then num to the 5, right, divided by the denominator is a certain big number. Okay, many digits. Then there is a command in GP-Paris, it's something that the masters would be very happy to have. I want to recognize this number. Let me call it alpha. Right? It's the guy above. I want to ask the computer, is this number close to a root of a polynomial of degree? I can ask for the degree. So let's say degree 5. Right? He's returning me a candidate polynomial, so it's an ugly polynomial, right? But if I go to degree 8, then I got this very nice output. Oh. So this output means the alpha above coincide with the root of this polynomial up to the precision of the computer. Right? And I ask for, I don't know, 500 digits. Okay, so it's not a proof, but it returns me the candidate, and then you can check afterwards that this polynomial really defines a unit lying in the number field above Q of I with ramification that's really prescribed by the input. For instance, yeah, I can ask what is the discriminant of this number field, at least, and then factor the discriminant. Yeah, so it has just ramification at 2 and 3. So it's, yeah, I mean, it's kind of evidence that it's the proper class, right? Okay, so that's CM theory. And illustrative CM theory in a sense. So the algorithm for algebra is based on LLM. It's a very, very convenient tool that's available to us. Okay. About Hilbert's 12 problem, there have been very few progresses, I would say, except for the p-adic. So in the, yeah, so first, Hilbert's 12 problem is partially solved in the case of a CM field instead of an imaginary quadratic field by Shimura's work. Okay. And in the case where the ground field is real quadratic or even totally real, then one needs to use p-adic approaches so far. So there has been successful work by Dasgupta Kagde recently, who proved the Grosstark conjecture. And in the case where the ground field is real quadratic, there is an alternative proposal and proved by Darmon-Pozzi and Wong. So that's when for the case where the base field is totally real. Right. But I want to go in a different direction. I want my ground field to be complex cubic in this talk. Okay. So for now on, my field K will be complex. I want to see it as sitting through its complex embedding in C. And so I have a Z basis 1 tau sigma with tau and sigma being both complex. Okay, and I would like to cook up certain function, maybe some kind of infinite product that would be relevant. And you will see that there are some candidates, but of course there is a very classical obstruction that there are no meromorphic functions that have 3 independent variables. Okay. Linearly independent variables over R. Okay, so still, the function that will play a major role in this talk is this elliptic gamma function that was introduced by physicists, more specifically by Ruijsenaars in 1997. It's given by this infinite product. So maybe I think it's worth, yeah, Nicolas called it the beautiful elliptic gamma function. So that it has, again, an elliptic variable, Z. So it's defined over C cross upper half plane cross upper half plane. And it is given by this very nice R to the K exponential Z, right, divided K. Z0. So formally, it looks like a bit like the theta0 function. Maybe also the G+1 is at the top. Kind of looks like the Jacobi theta function, except that it is a ratio and except that it is different. But, yeah. So that's one function and that's the other. I will try to explain in this talk that this function has kind of symmetries under SL3Z and that it is relevant to Hilbert's 12 problem. So first, the little bit of physics that I should say about it is, okay, it's this sentence that I love in the experiment.
Is it some exactly solvable Baxter model that it's solution of, you know? I mean, you.
Oh, no, I cannot answer anything about the physics underlying this function. Even though I will try to explain you that this is a necessary function for the toolbox of number theorists. So that's the aim of my talk, trying to convince you that we had to come up with this function at some point. And that's, yeah, so rather than discuss its origin in physics, I would like to motivate this very definition by providing some kind of historical perspective about it and try to convince you that it is a natural candidate for the requirements of Kronecker and Hilbert. I would like to argue that this function or its avatars might have been anticipated by Eisenstein as early as 1844. So let me discuss Eisenstein's forgotten paper. So as early as its definition of Eisenstein series, Eisenstein noticed, so he was 20 years old when he wrote this paper. So that's I'm calling this the Jugendtraum, he noticed that this series diverges because it has 3 PLA. Right? But in this very same paper, he first considers products rather than series. So he would write down many products, and I'm following his discussion here. So he will write down the one-dimensional infinite product. So you go to series by taking log, of course. So product I's means you take convergence through symmetric products, right? Between minus n, and then limit when n goes to infinity. Then the output from Euler is 1 minus this over 1 minus this up to some exponential 2 pi i's. So that's the cyclotomic case in a sense. Okay, there is this exponential factor here. And if you do this game with double products, Eisenstein explains you that the output is the theta 0 function, even a ratio of theta 0 function. So he was pleased by this, and of course, he writes the following. In the higher dimensional case, he writes down that we should consider as a higher analog of as an analog of higher degree. Here I emphasize quotients of infinite triple products of the following shape, where you just generalize, right? But of course, he was very much aware that this diverges, so one cannot assign all values to lambda, lambda prime, lambda second. Okay. But everything is not lost, because he made the suggestion. He says the following: no such inconvenience, meaning divergence, arises if we impose some restrictions to the indices, such as inequality conditions. So lambda, lambda prime, and lambda second will be subjected to inequalities. And if you do so, then there is a large class of such functions that is closely connected to number theory. They possess remarkable properties, and they lead to the most beautiful researchers, and seem to lie at the crossroads where the most difficult parts of analysis and number theory meet. And I want to notice here that the sentence has kind of the same flavor as Hilbert, because Hilbert meant that 3 branches of math were joining through his problem. So here, Eisenstein anticipated these kind of sentences, and he seems to have more than just a wish. He seems to have something about this kind of products. I will try to discuss how much he might have possessed. So in this paper also, Eisenstein mentioned a specific kind of inequalities, the inequalities arising from certain geometric progression. So in my dictionary, I would like to think about these inequalities as connected to the fundamental unit of a complex cubic field, as defining a certain cone, maybe. Anyway, so a little bit of historical aside. Eisenstein and Kronecker were friends and working together in Berlin. So one might ask, maybe the Jugendtraum of Eisenstein and of Kronecker might be related in some way. And this paper of Eisenstein has been ridiculed by Jacobi, and thus, maybe thus, I don't know, at least it has been ignored in the many years after this, and I think it needs to be reevaluated. So actually, I will have the quote of Jacobi. Jacobi wrote, the year after, he wrote, Mr. Eisenstein said that by analogy in the theory of abelian integrals, we should consider quotients of quotients. But what are quotients of quotients? They are simply quotients. Yeah. Not a very subtle, yeah. Not a very subtle. Anyway, so that's the state of affair, because Eisenstein never came back to this topic in his short life. So my first aim in this talk is to try to bridge the gap between these triple infinite products and the gamma function that's written on the blackboard. Okay, so by doing maybe some heuristic, but still I think it's meaningful. So I will follow Eisenstein 2 advices. One of the advice is you need to take quotients of quotients, and you need to use inequalities. So I'm taking a triple product indexed by inequalities, right? And I'm doing the same smoothing that was achieved for the theta function. I'm taking the initial product raised to the power n, and then
Lambda primed and lambda double primed in what?
in z, yeah, in z, but both positive. But the first one runs over z, okay? And I want to think about this product as not being absolutely convergent. I want to do the product over z first, okay? So this is a rational fraction, quotient of rational fraction. But if I order the product, then by using the formula of Euler, remember that formula, then the ratio, the smoothing has the nice property that you get rid of this annoyance exponential pi z. And so you reach immediately the following product. You get rid of that one that turns rational fractions into 1 minus exponentials, right? And when you are there, lambda and lambda prime being both positives, it's much closer to this. So this is called, I would call it Q plus plus. Then there is a Q minus minus with a similar inequality opposite. And when you do this ratio Q plus plus over Q minus minus, then it follows from the definition that it is indeed a certain ratio of the gamma function. So if you play the game of Eisenstein, I would say you are inevitably led to this kind of gamma ratio. Okay.
But so far, there's no role played by the fundamental unit yet.
No, there is no arithmetic yet. Yeah. Later on, the inequalities will be more sophisticated than this. Yeah. There is no cubic field yet. Yeah. It's the beginning of the talk is function theoretic. Yeah. So the summary so far is that this smooth ratio of the elliptic gamma function can be constructed at Eisenstein in a similar way, similar to the ratio of theta function. Okay. And now I want to turn to my live demo. So I want to evaluate this function and try to convince you. I will evaluate the function on top at certain cubic arguments and try to convince you that they might be the function that Hilbert was asking for. Let's see. Yeah, so the input data will be this. I fix a certain cubic root of 7, a complex cubic root of 7, that one specifically. And my tau 0 will be that guy that, okay, it belongs to H lower, but it's fine. And it belongs to the cubic field as well. Okay, that's what tau 0 is. And that's what sigma 0 is. Okay, there are some, I will try to explain later how you can up with these values, but these together with one built up a z basis of a certain fractional ideal of my complex cubic field. Okay, and I want to compute this ratio. So again, it is at v0 equal 1/3. I compute this gamma value raised to the 5th power divided by same gamma value, each argument multiplied by 5, right? And I want to show you that the code is good enough to compute this very efficiently. Okay, so the number field is cubic root of 7. Beta is the complex image of the root. And then I have my, I want to compute two values. One is the numerator and the other is the denominator. Okay. So less than 1 second. I think I have 500 digits. And then I want to do algebra of the ratio. Numerator to the 5 divided by denominator, nothing. Let's say degree 8. It's not nice at output. Then if I go to 18, then I got something much nicer, right? So this means that the gamma ratio below, what do we see it? The gamma ratio below there. this gamma ratio is up to 500, or it could be 1000 digits, is a root of this polynomial, which is actually irreducible over Q. It defines a unit, it's very much symmetric, it's reciprocal. So out of this complex number and using its inverse and its conjugate, you got in the end 4 roots of this degree 18 polynomial.
Sorry, how does the 5 depend on the input data?
The 5 is the smoothing thing. So it's sort of an auxiliary data that, in terms of ramification, what really counts is the denominator of V0. So the ramification is at 3 only. Let me check if you want to see the ramification. So that very nice polynomial has ramification only at, so 7 is because of the ground field, and then 3. And it's because of this V0 being 1/3. So as a parallel to the theory of elliptic units.
Yeah, but why is it 5?
Why is the 5? Yeah. I could have chosen other smoothing. I need to smooth by a prime number in our construction, but the smoothing is there to get rid of the exponential pi I z factor in the transformation formula of the infinite product.
It's just a random prime number.
It has to be totally split in the cubic field. Yeah.
Sorry, can you just show us what are tau and sigma exactly?
Yeah. Let me get back to there. Yeah. It corresponds to a certain fractional idea, in fact. So mostly what we do, we start with a fractional ideal of K, and we pick a certain Z basis that's well suited to the situation. I will explain how to pick basis later on.
And how do you compute this elliptic? Are you just using this product or
Yeah. As long as you are high enough in the upper half plane, it converges pretty fast. Yeah. So not enough. Not only can we compute one value, but we can compute as much as we can roots, as many as we can roots of this polynomial. Back. Yeah, we want to try to parameterize all the roots of this polynomial. So there are, so that's the story about what I displayed for you was the story for this polynomial over Q, but in fact you can find out what's the polynomial over K. Okay, so it's the degree 6, irreducible of degree 6 over K, and it generates a specific abelian class field of K. And all the roots of the same polynomial are given by these gamma values. So the Galois group, the action of the Galois group on the former algebraic number translate into the evaluation at some other points that you can very specifically write down. So you compute this gamma value, and together with inverses and complex conjugates, out of the 18 values of the, you got 2/3 of the values of the roots of the polynomial of degree 18. The other values are on the unit circle, and for these values, we don't have any formulas. But for the other 12, we have formulas of the shape of certain gamma values. Gamma ratios, I should say, right? Yeah, quotient. This is a quotient, and I'm taking quotients of quotient. Whatever Jacobi.
It's a bit like Charollois-Selberg in the sense that you take gammas at special values related by Eisenstein series. You don't have any more comments. You never talk about Charollois-Selberg.
No. Unfortunately, I don't have much to say yet about Charollois-Selberg.
I mean, if I read gamma, we should think of gamma as the extension of some generalization of the gamma function, right?
So you can translate these statements about the gamma value to a statement about Q++ over Q minus that I described as arising from Eisenstein's triple products, and you get also some algebraic conjecture. Okay, it's all about conjectures for these values to be algebraic and to be defining units. Okay. So I want to state the general conjecture. This was just one specific example of algebraicity, but to state the general conjecture, I need to tell you a bit more about this gamma function that was introduced by physicists and studied more deeply by Felder and Varchenko. This function has certain internal symmetries that makes it an analog of theta 0. And this function is just part of a whole family of functions indexed by pairs of primitive vectors in Z3. So A and B will be primitive vectors in Z3. Z will be again an elliptic variable, and X will be in P2C, well, let's say in C3, P2C minus P2R. And the whole collection will satisfy a one cocycle property I will write down for you in the coming slides. Okay, and everything is about being a cocycle under SL3Z. The underlying group really is SL3Z for this function. That's what Felder and his collaborators were able to establish. So first, the periodicities. So it's one periodic in actually all the variable. And notice, yeah, this is very interesting. It's almost tau periodic in Z up to a factor that's theta 0. And there is a whole hierarchy of, remember that theta 0 was almost periodic up to exponential 2 pi I. That one is up to theta 0. And there are higher dimensional generalization where, say, for SL4Z, it's almost periodic up to the function for SL3Z. So there is a whole generalization of such functions. The obstruction being given by the previous one. And now for the modularity property, so when SL3Z is acting on P2C, here is a sample of the relation that gamma satisfies. So 3 terms relation, it's almost 1 up to exponential 2 pi I times a polynomial in Z of degree 3 with rational coefficient. So very much of a Bernoulli polynomial. With, yeah, actually a product, yeah, okay. So, yeah. The coefficients involve Bernoulli numbers. Say. So very reminiscent of the transformation formula for theta Z. That was established by Felder and Varchenko. And now the cubic field will enter the picture. I will define what kind of arithmetic gamma functions. So the fundamental unit will come in, and I will first describe the family of functions gamma AB, and I will choose A to be a certain base point in Z3 primitive, and B will be epsilon times A. So that's my pair of vectors as an input. So how I will choose A depends on epsilon. So I want to start, yeah, with two ideal. That's my conductor, and that's the ideal that will index the partial zeta value, yeah, and coprime ideals. The fractional ideal will be F times B minus 1. And the fundamental unit, I want to pick it as being congruent to 1 modulo F. And there is some normalization there, okay. Q is the order of 1 modulo L. Now, I want to pick a Z basis of my lattice, of my fractional ideal, in such a way that it is adapted to A. Okay, so that's the elementary divisors theorem. It's possible to choose such a basis as long as A is a prime ideal. So that's my only condition on A. For the smoothing prime ideal, I want it to be prime, and there is a further congruence condition. Okay, so it's always possible to pick a basis, a Z basis of L, this way. And once you have picked this Z basis, the choice of A is forced on you by certain duality statement. So I have this E3 as a target there, and given epsilon, there is a unique A such that this is an element of the dual of the dual. So there is a unique A that's primitive up to sign, and then there is a second condition that about choosing A between minus A, so certain orientation condition. Okay, so given epsilon again and E3 and gamma, there is a unique A. And we can draw the pictures about this. So again, my gamma is E3. I have gamma is generating the intersection of the kernel of A intersected with the kernel of epsilon A. Okay, so that's a line. And then I pick certain supplementary bases, alpha and beta, with certain positivity condition and orientation condition. And out of this data, I will build the gamma AB. So gamma AB is a finite product of the gamma values. So it's meromorphic. It's defined on C3 except certain hyperplanes. And this finite product is indexed by certain elements that are a finite number of elements. It's finite because everything is up to elements that vanish on both A and B. Okay, so it's a finite product. When A and B are the elements of the first elements of the canonical basis, it's just the gamma function that I displayed on the right hand side. Okay. The number of terms in this product is depends on the Hermite normal form of A and B. So yeah.
So to make sure that you have the adapted basis that you claim, don't you need the norm of A to B prime, not just A to B prime?
You are right.
Because you have the index to be prime, right?
Yeah. I want the norm of A to B prime. Yeah, exactly. I want this to be cyclic, in fact. So it could be actually a norm of prime, and it's okay. Yeah, I want something cyclic. Yeah, you're absolutely right. Okay. So I have this finite product, and that are the gamma ABs that are defined by Felder and his collaborators. And now it's very nice to explain what's the SL3Z properties for the gammas. When G in SL3Z is acting on both A and B and X in C3, then you recover the gamma AB at X. So if that's the equivariance property, and the one cocycle relation is this: gamma AB times gamma BC times gamma CA is exponential times pi I times the polynomial of, depending on ABC, and this polynomial is of degree less than 3 in the last variable. Okay. So I want to think of this identity as there is a certain 2 cocycle on SL3Z that takes values into rational polynomials or rational fractions. And this 2 cocycle, the exponential of pi I of it, is transgressed, as Nicolas would say, is transgressed by the gamma AB, or split, if you will. Yeah. There is one cochain that split this exponential pi I times the cocycle. Does not make it trivial. The class of this is not trivial, right? The right-hand side is algebraic, but the left-hand side is some kind of transcendental function. And this way, it kind of makes gamma AB an analog of the Dedekind eta function, if you want, where here you will have the Rademacher cocycle for SL2Z, and the left-hand side will be the log of eta function, or log of theta 0 function. Okay. So, yeah, this kind of explains the occurrence of the gamma AB if you start with the PABs. Okay, now I want to evaluate my gamma AB at a certain tori. So B will be epsilon A. And A arises from the previous lemma. So that's what the algebraic invariant wants to be. It wants to depend on this data. Okay, I want to evaluate at A epsilon A, and then the X is the image of E1, E2, E3, my Z basis under the complex embedding. So these are the X has 3 coordinates that belong to K. And then the first elliptic element is a certain element in K again, and I will smooth it. So I take gamma to a certain power divided by gamma with the lattice being modified by A. So in the case where A and B are E1, E2, it really boils down to the numerical example that I explained to you just before. Okay? And our general conjecture about any complex cubic field and given fractional ideal and with adapted bases this way is actually fourfold. So this invariant as a complex number does not depend on gamma. There is the base point does not depend. The output does not depend on the base point. And we conjecture that as long as A is co-prime to 6 normal, then gamma at L is the image of a certain unit lying in that specific class field of conductor F above K. embedded in C. The embedding is one of the embedding extending the fixed embedding of K in C. Okay, so we got complex numbers that are images of algebraic numbers. And the other root of the minimal polynomial of U, the one that are above a real embedding of K, it is part of the conjecture that they lie on the unit circle. There are complex numbers lying on the unit circle. And we also state a certain reciprocity formula, much of the same flavor as in the case of imaginary quadratic field. Okay, so what kind of reasons do we have to believe in this conjecture? I have showed you some numerical computation, but so the computation that was made for you was set up for this specific field with A of norm 5 and F of norm 3. For that example, I chose it. So there is a little bit of there is a lot of cherry picking in the examples. They are appealing if I find them more appealing if there is only one ratio of gamma function. Okay. So that the product for over classes of F modulo Z gamma boils down to one element. And I like this. I would like to state this problem as a nice question. What are the fields? So what are the cubic fields? So that this evaluation actually has only one single term, because for my computer it's much better, and it's not as important as the class number 1 problem. It's kind of a nice, interesting.
Has it got any connection with the class number? You know,
I don't know. I want to raise this question. So yeah, it really depends on both the I think maybe the class number of K and the shape of the fundamental unit really. Okay, and we have dozens of examples with many digits and with quite high degrees, but there is no hope yet to have tables. Okay, it's we have to pick the cubic fields so that the unit is quite nice, and the algorithm is not robust enough yet to compute with arbitrary cubic field. It's still very much depending on how the input behaves. And so designing a nice algorithm, there is, for instance.
But you have checked cases where the class number is not 1.
Yeah. Does not depend so much does not depend on the class number of the cubic field, but for SL2Z there is a nice algorithm that puts a point as high as possible above the real axis. Here, for the action of SL3Z, it's not so clear. The tau could be high, but the sigma would be low. So even what is the nicest statement about the position for tau and sigma is not so obvious. So I leave this question as an open question to find nice fundamental domains for these actions. So another evidence for the conjecture is a theorem, of course. So in the classical case, there is the Kronecker limit formula that relates over imaginary quadratic fields, the partial zeta functions for this Z module of rank 2 to the log of modular units evaluated at tau 0. Okay, that's exactly the statement of the first Kronecker limit formula, or second if you want to work with theta 0. And in the cubic setting, what we came up with is a certain linear combination of two partial zeta functions. So the partial zeta function attached to the class B is the summation over all C integral ideals equivalent to B in the ray class group modulo F. And we twist it by norm of A, and then we subtract the partial zeta function attached to the product AB. So that we have systematic vanishing at S equal to 0. And when we do this, then unconditionally, okay, it does not depend on the conjecture anymore, we can compare the first derivative of this twisted partial zeta function at S equal to 0 to the logarithm of our analytically defined gamma invariant. Right? And the statement of the theorem is an equality up to sign between this and the logarithm of the absolute value of our complex invariant. Okay. And the sign, if you orient properly, you can even sort out what the sign is.
And the proof of this?
The proof relies on certain Eisenstein series for GL3, but I would say they are non-standard. And Nicolas came up with them, and I have.
Okay, so Eisenstein's back.
Eisenstein's back, and you compute certain period of these Eisenstein series over certain geodesics for the symmetric domain for GL3R, and then you deform the path of integration. So if you consider this identity, then if you believe in Stark's conjecture, and I'm part of the believers, then the left-hand side should be the logarithm of a certain, or the absolute value of a certain unit lying in an abelian extension of K. And so our formula for gamma A is a refinement of Stark's conjecture in the sense that we provide a formula not only for the absolute value of the unit, but for the unit itself. In terms of holomorphic function, this is, to my taste, it's better than a zeta function, right? It wants to be a modular object that parameterizes algebraic numbers. So so that theorem is a way to state that our conjecture is compatible and the refinement of Stark conjecture. Okay.
I see the compatibility, but your theorem plus your conjecture completely implies the full statement of Stark, or is there some technicality that I'm missing?
I'm tempted to say so, but in Stark conjecture, there is also the statement about, our conjecture is inspired by Stark conjecture. So I don't think we claim more. The conjugate for the units above the real place are on the unit circle. This is part of Stark conjecture. There is a statement in Stark conjecture about certain square root of the unit defining an abelian extension over K. There is a subtlety in the Stark conjecture that I'm not sure I really understand, so we discard it.
So also check has a refinement of the Stark conjecture, right? Does this have a relate?
It's coming next slide. So I want to put this work into a broader context, namely the context of Hilbert's problem in the case where the ground field is an ATR number field. That is a number field that is almost totally real, by which I mean it has exactly one complex embedding. Okay, so I'm not an expert in Hilbert's problem above real quadratic fields. What I mean is I need one complex embedding to work with. So imaginary quadratic fields are good, complex cubic fields are good, and more generally, any degree n extension of a Q having exactly one complex embedding. Then I'm in good shape to play this kind of game. So there has been various approaches to this setting. So we were inspired by the work of Wren and Sech over complex cubic field again, and they were able in 2009.
Given what you've written there, is that function not related to a Barnes double gamma?
I think it is. Their construction was based on Barnes gamma function, and the Barnes gamma function are attached to a cone. So the summation is over n cross n cross n. So, and whereas our summation is related to n cross z. So in a sense, I would say that this gamma function is the sum of two Barnes gamma functions so that the cone contains a line. And then if you look at their statement, they have some joint term that they want to discard. And I think there might be a combinatorics argument so that their conjecture, if you apply it to two cones and you combine two cones together, then the joint goes away and you end up with this function that have one periodicity in Z.
But I don't remember the Barnes double gamma function having any higher degree modularity like you're describing here, right?
No, I think you need to be able to apply Poisson or do something. You need to have some Z line sitting in the to be in order to have nice modularity properties. You need to have at least one Z line sitting in the code. So they are very much related, these works, but the functions look different, and the symmetries for SL3Z we do have. So yeah, and they would fix a certain Shintani fundamental domain, but that kind of amounts to my choices of A and epsilon A, and the fact that we have a cocycle makes it clear that it does not depend on the choice of the base point in a sense. Yeah. So whereas they would need to say that if you change your fundamental domain, why do you get the same invariant? It's not so obvious for Shintani construction. Another setting where the ground field was ATR was my work with Henri Darmon, where the ground field was quartic over Q. K was ATR, so it had two real places and one complex embedding, but there was an underlying real quadratic field. Let's say Q square root of 2. And we were able to refine the Stark conjecture over K by using the Hilbert modular group. And more specifically, the weight 2-2 Eisenstein series there. By combining certain periods and certain derived periods for the weight 2-2 Eisenstein series over the Hilbert modular group, we kind of had a one cocycle for the Hilbert modular group that was evaluated at some tori, so some rank 1 tori related to the relative unit for K over F. And then we were able to get some refined Stark's units, Stark conjecture in this specific setting. But we took advantage of the fact that there was, it's not all quartic fields, not all quartic ATR fields do have an underlying F. That's quartic real. And finally, I want to mention that my student Pierre Morin is doing ongoing work where he's also studying the case where K is ATR quartic, but now instead of using the Hilbert modular group, he's using really the underlying group SL4Z. So forget about this underlying field, and by using SL4Z and the higher dimensional analogues of the elliptic gamma function, so yeah, it would be a function that has more variables, right? That would be a tau1, tau2, tau3. And by evaluating this gamma function at tori of rank 2 now, he already has some numerical examples where he got units lying above this kind of field K. So it would be, yeah, it is tempting to guess that the general case would be a degree n ATR number field, and using SLNZ and multivariable gamma functions, then one should be able to get units lying above there. So by working exactly at the complex embedding of the field K, and seeing all the evaluation going through this complex embedding of K. There is already the hierarchy of function that is available to us. So there are a lot of people have been extending the work of Felder and Varchenko. So the functions are available to us. The evaluation and the algorithm are very much, it's ongoing work. And I think I reached the end of my talk. Thank you for your
Are there any questions?
In the general case, there is a relation between this derivative of theta function that is equal to 0.
Expected, yes, but I think it's going to be tricky. It should be true, but the proof is not going to be obvious at all.
You cannot go back to Shintani metric.
Maybe, but again, it would be first a Shintani domain for an ATR field. So yeah, usually Shintani domain are for totally real field. It's true that there are some extensions, but already no, it's not straightforward at all.
Can you say a bit more about what Eisenstein series you used on SL3 in the proof of the?
In the proof, I think it's a non-standard one. I have to look at it. No, Yeah. We need to look at the paper closely, but it's
Is its meromorphic continuation? Do you require to quote something fancy, or is it follow from some?
no, I think when you integrate inside the symmetric domain, the zeta value pops out, but to get the elliptic gamma function to come out, you need to push the cycle to infinity, and then everything splits up as a product of dimension 1 thing, and then you apply you get the Bessel function.
Okay.
You get back to apply 3 times the Kronecker limit formula in a sense. Yeah.
Can you say something more about the higher dimensional elliptic gamma functions?
Yeah. Yeah. It's so typically okay, let me modify this. I would GK and then L, and then you would have S to the L. So it's true that depending on if the dimension is odd or even, things occur as products or ratios. So dimension 3, it's not clear to me anymore. And maybe there is an extra term on top. But my main point is that the obstruction really is that gamma for SL4, let's call that guy gamma 3. Yeah, my former gamma would be gamma 3. So gamma 4 at Z plus tau 1, tau 2, tau 3 is equal to gamma 3 at Z tau 1, tau 2, tau 3, 4 of Z tau 1, tau 3. And it's going to be a meromorphic function that has poles at Z plus N tau 1 plus N 2 plus N tau 3. So that's not dense. And it will have poles there and zeros at the opposite guys. And with these properties, I think it kind of characterizes it uniquely up to a constant, and there are ways to normalize it. So there is really a whole hierarchy, and the poles and the zero are located on certain rational hyperplanes. Always a Z line only as a periodicity line. Nice Fourier expansions and nice, but the symmetries, yeah, the symmetries is under SL4Z in the sense that you would have gamma. That will be gamma at E1, E2, E3, E. Yeah, and then the two cocycle relation will take the shape gamma BD, gamma A CD, gamma B CD. It's a 4 term on the left will be exponential 2 pi I, a certain polynomial at Z. And that builds up a class in H3 for SL4Z with coefficients that are polynomials or rational fractions. And this 3 cocycle for SL4Z is transgressed by the higher dimensional gamma function. Okay. And then you need to evaluate that's a multiplicative 2 cocycle, and to produce algebraic invariant, you will evaluate this multiplicative 2 cocycle at a rank 2 tori arising from an ATR quartic field. That seems to be the combinatorics underlying.
Sorry, if I can ask something else. I mean, you're mentioning this like rank 2 tori. Is there hope of proving your analog of the Kronecker limit formula? Like the proof seems to like use very like fundamentally the fact that your torus is rank 1. Right, so rank 2 tori, like the problem becomes much harder.
Yeah.
So like, is there hope of trying to get a similar result?
There is hope, but it will take it will take people having strong technicalities, I guess. Yeah. Yeah, it's true that line integrals are much.
So are there analog of gamma functions whose symmetry is described by other reductive group instead of like SL?
We should ask physicists again, because I have no, yeah. Could be. I don't know. Good question.
SP form embeds into SL form.
No, I mean, like,
No, I
not,
understand, I
not,
understand.
yeah.
Yeah, so the symmetric space for GL3Z plays a role hidden in the indices ABC, in a sense. The function takes values. The function takes an argument in P2C, right? It's holomorphic function of the over P2C minus P2R, or certain opens there, but it's not a function defined over this symmetric space of real dimension phi, right?
There are no more questions. Let's thank